Welcome to G Fun Facts Online. Today, we're diving into the most violent events known to humanity since the Big Bang itself, gamma-ray bursts. Imagine our sun's entire 10 billion-year lifetime of energy, unleashed in a matter of seconds. That's a gamma-ray burst, or GRB. For decades, astronomers thought they had these cosmic behemoths figured out, sorting them neatly into two boxes. But a growing number of cosmic rebels are breaking all the rules, forcing us to rethink the very laws of physics and the kinds of bizarre objects that might lurk in the universe. To understand the mystery, we first need to understand the Standard Model. Since their accidental discovery in the 1960s by satellites looking for nuclear tests, we've learned that GRBs come in two main flavors, distinguished by how long they last. First, you have the long-duration GRBs. These are the more common type, lasting longer than 2 seconds. The consensus is that they are the death cries of truly massive stars, at least 25 times the mass of our Sun. When such a star runs out of fuel, its core collapses under its own immense gravity, forming a black hole. This process, called a collapsar, isn't a gentle fade-out. The star is typically spinning rapidly, and as its material spirals into the new black hole, it forms a superheated, swirling disk. This disk acts like an engine, launching twin jets of particles at nearly the speed of light. These jets have to punch their way through the star's outer layers. When they finally break free, they blast out a focused beam of high-energy gamma rays. If one of those beams happens to be pointed at Earth, we see a long-duration gamma-ray burst. The second category is the short-duration GRBs. These are fleeting, lasting less than 2 seconds. For a long time, their origin was a puzzle, but the leading theory, now backed by incredible evidence, is the merger of two ultra-dense objects. Imagine two neutron stars, the collapsed cores of smaller massive stars, or a neutron star and a black hole, locked in a gravitational dance. As they spiral closer and closer, they whip around each other at incredible speeds before violently colliding and merging. This cataclysmic event forms a new, larger black hole and releases a tremendous, concentrated blast of energy in a short, intense burst of gamma rays. This theory got its rock-solid confirmation in 2017 when the LIGO and Virgo observatories detected gravitational waves, ripples in spacetime, from a binary neutron star merger. Just 1.7 seconds later, space telescopes detected a short GRB from the exact same spot in the sky. It was a landmark moment for astronomy. Following the main gamma-ray flash, most GRBs also produce a longer-lasting afterglow in lower energies like X-rays, visible light, and radio waves. This happens as the relativistic jets slam into the gas and dust surrounding the event, creating a shockwave that can glow for days, weeks, or even months. Studying this afterglow is crucial. It helps us pinpoint the burst's location and understand the environment it came from. So for a while, the picture seemed clear. Long bursts from dying giant stars, short bursts from merging dense objects. But the universe, as it often does, had other plans. A growing collection of GRBs are refusing to fit into these neat categories. These are the rebels of the cosmos, the unexplained bursts that are challenging everything we thought we knew. Some of the most perplexing are the hybrid bursts, which show a confusing mix of features from both long and short GRBs. Take GRB 211211A. This burst lasted for over 50 seconds, placing it squarely in the long-duration camp. According to the rulebook, it should have been followed by the bright, fading light of a supernova, the explosion of the parent star. But it wasn't. Instead, astronomers found a kilonova, a fainter, reddish glow powered by the radioactive decay of heavy elements. Kilonovas are the signature of a compact object merger, not a collapsar. So we have a long burst with a merger's afterglow. How is that possible? One idea is that it was a merger between a neutron star and another compact object, which somehow managed to sustain a jet for a much longer time than expected. Then there's the famous case of GRBO 60614. It lasted 102 seconds, definitely a long burst. But, just like a short burst, it had no accompanying supernova. Its light pattern also looked more like a short burst. The event was so baffling, it led some scientists to propose we need entirely new classification schemes. More recently, GRB 230307A blurred the lines even further. This was the second brightest GRB ever detected, and it went on for about 3 minutes. A clear, open and shut long GRB, right? Wrong. The James Webb Space Telescope turned its powerful eye to the afterglow and found the unmistakable chemical fingerprints of a neutron star merger, including heavy elements like tellurium. This was a bombshell. It strongly suggests that mergers, which we thought could only make short bursts, can somehow produce long ones too. This was a scenario previously thought to be impossible. The anomalies don't stop with hybrids. Meet GRB 200826A. This burst lasted just 1 second, a classic short GRB. But when astronomers traced it back to its home galaxy, they found it came from a region of active star formation, the typical birthplace of the massive stars that create long GRBs. Detailed analysis suggested it did, in fact, originate from a collapsar. So why was it so short? The leading theory is that it was a fizzled burst. The jet of energy formed in the core of the star, but it struggled to punch through the star's thick outer layers. It almost made it, but petered out, producing only a brief gasp of gamma rays instead of a long scream. On the other end of the spectrum are the ultra-long GRBs. These can last for thousands of seconds, sometimes close to an hour. The standard collapsar model just doesn't work here. The engine that powers the jet, the accretion disk around the new black hole, should NT be able to stay active for that long. This has forced theorists to consider other progenitors, like the collapse of a blue supergiant star. These stars have much larger, more diffuse outer envelopes, which could provide a sustained fuel source to power a jet for an exceptionally long time. But perhaps the most mind-bending discovery of all is GRB 250702b. Observed recently, this event wasn't just ultra-long, lasting for nearly a full day. It also appeared to repeat. This has never been seen before in over 50 years of GRB observations. Gamma-ray bursts are supposed to be cataclysmic, one-off events. A collapsar destroys the star. A merger destroys the two objects. There's nothing left to do it again. A repeating GRB is a profound mystery that no current model can adequately explain. It fundamentally breaks our understanding of what these events are. These cosmic rebels have sparked a firestorm of new ideas. Astrophysicists are now proposing a menagerie of exotic objects and phenomena to explain these outliers. One of the most promising candidates for the engine behind some of these weird bursts is a magnetar. A magnetar is a special type of neutron star with a magnetic field trillions of times stronger than Earth's. If a cataclysmic event, like a merger or a special kind of collapse, creates a rapidly spinning, highly magnetized magnetar, it could act as a powerhouse. The energy released as this magnetar rapidly spins down could sustain a GRB jet for a much longer time, potentially explaining ultra-long bursts and some hybrids. An even more exotic idea is the quark star hypothesis. Under the immense pressure inside a neutron star, theory suggests that the neutrons themselves could break down into their fundamental components, quarks. The sudden conversion of a neutron star into a so-called quark star, a process dubbed a quark nova, would release a staggering amount of energy and could be the source of some GRBs. This model is intriguing, because it could potentially explain a variety of burst types, all from the same basic process. Other possibilities include a star being torn apart by a black hole in a tidal disruption event, or the merger of a neutron star with a white dwarf. It's clear that the simple two-category system is no longer enough. The key to solving these mysteries lies in a new era of investigation: multi-messenger astronomy. We're no longer just looking at light. We're using gravitational waves, neutrinos, and cosmic rays to build a complete picture of these events. Gravitational waves, the ripples in space-time, give us a direct window into the central engine. The 2017 detection of waves from a neutron star merger confirmed their link to short GRBs. For the new hybrid bursts, future gravitational wave detectors could listen for the specific signature of a collapsar versus a merger, telling us exactly what kind of engine is at work. Then there are neutrinos, the ghost particles. They are produced in the same fiery cauldrons as GRBs, but barely interact with matter, meaning they fly straight out from the heart of the explosion. Detecting high-energy neutrinos from a GRB would be a smoking gun, confirming our models of particle acceleration in the jets. So far, a definitive link hasn't been made, but observatories like IceCube in Antarctica are constantly on the hunt. The future is incredibly exciting. The upcoming Cherenkov telescope array will see GRBs in higher energy gamma rays than ever before, testing our theories with unprecedented precision. The Vera C. Rubin Observatory will scan the entire sky every few nights, making it a powerful machine for finding the faint, fading afterglows of these bursts moments after they occur. By combining the power of these new instruments with the insights from multi-messenger astronomy, we are on the verge of a revolution. These unexplained gamma-ray bursts, once a source of confusion, are now a golden opportunity. Each new anomaly is a clue, pushing us closer to understanding the most extreme physics in the universe, and maybe even discovering new laws that govern it all. Thanks for tuning in to G Fun Facts Online.